Well, good evening, everyone. This is Gerald McKeegan up at the Chabot Space and Science Center. Give us just a couple of seconds here. We're still getting set up. We're up here in our 36-inch telescope, the one we call Nellie. Now everybody else is here now too. We're still doing some camera setup, so bear with us. It's Saturday night, June 19th, and we have clear skies here at Chabot Space and Science Center. And we have relatively low humidity. It's only about 42%. So it looks like a good viewing night. How we doing, Rick? You got the camera all set up yet?
We're able to do the live view for the moon, which is the first part of our program, but we may have to swap things out for the second part.
So, yeah, having a little technical problems there, Gerald.
All right. Okay. Well, I want to remind everybody before we get started here. Our virtual programming is being presented to you in lieu of live visits to the Chabot Space and Science Center. Chabot Space and Science Center right now is closed to the public. We will reopen the Space and Science Center in the fall. In the meantime, we're doing lots of virtual programming like what you're watching now. We're also hosting very small private rental events up here as well. So we are slowly working our way back into it, but we're really looking forward to our grand reopening in the fall when we will start our partnership with NASA. But in the meantime, we are doing lots of renovating of the facility. And of course, since we don't have regular visitors coming in, we don't have the revenue that we would normally get from that. So we do ask that you help us out by supporting us with a donation. If you're on the Facebook page, you'll see a donation button somewhere around the comment section. You can also go to Chabot's website, which is chabotspace.org. And at the top of the page there, you'll see a donate button as well. So if you get a chance, help us out. We would really appreciate it. So how are we doing, guys?
Well, we'll be fine for the first part of the program, and we'll probably take a break midway to swap out computers and see if that fixes the problem for the longer exposures.
Okay. Yeah. Okay. So the first object we'd like to look at tonight is the moon, and I believe we are on the moon. Yes, we are. So the moon is at the phase we call waxing gibbous. Each night, a little bit more of the moon is being revealed by the sun. And this is probably among my two most favorite times to look at the moon is waxing gibbous, when there's still a little bit of the moon is dark. And the other time, of course, is when it's a thin crescent moon. So if you look at the image here, Rick, can you take the grid off of there? There we go. Thank you. So to the left, you see it's dark, and then to the right, it's light. The boundary between it is called the terminator. And what you're looking at is that portion of the moon to the right, which is in sunlight, and the part to the left is in darkness. And that terminator, the position on the moon, changes each night. And that's because of the orbit of the moon around the Earth. As the Earth orbits around the Earth, the angle between the sun, the moon, and the Earth changes. And some nights we see more, some nights we see less. That's what causes phases of the moon. So I'd like to do just a quickie tour. I'm going to move the telescope here, Rick, so don't panic if you get moving.
Okay, Gerald, sounds good.
All right, so kind of going up to the top here a little bit. And Rick, you're going to have to point things out as I talk about them, so hopefully I can direct you a little bit. So let's start out with that big round smooth thing right there. Yeah, that's the crater Plato. Crater Plato is an old impact crater, and it's right at the rim of a large dark area you see there called the Imbrium Basin. And the Imbrium Basin actually just below your cursor, just below the crater. That's the Imbrium Basin right there. The Imbrium Basin is a giant impact crater. And when that impact occurred, it cracked the crust of the moon. But this was 3.5 million years ago, maybe even 3.8 million years ago, at a time when the moon still had a molten interior. So what happened is those cracks caused lava to ooze up from the interior and fill that giant impact crater called the Imbrium Basin. And then the Plato crater, which was at the rim of the Imbrium impact basin, also filled with lava at the same time. So that round, very smooth floored crater that you see, that's the crater Plato. Going to go up and to the right a little bit, Rick, that smooth area there that you just kind of ran your cursor through, that's Frigoris, Mare Frigoris. And then just to your right of your cursor, you'll see two craters. And let's see, what are those two craters? Bear with me just a second here. Oh yeah, that's the
ones on the left?
uh,
Isn't that is that Endymion?
no, that's way over here, way over to the right. Yeah, so the upper one is Aristoteles, and the lower one is Eudoxus. And then coming down to the right of Plato, you see a mountain range. And that mountain range, a little bit to your left, Rick.
My left?
Yeah. And then up that mountain range between Plato, right there it is. Okay, so the mountain ranges on the moon are given names, and they're often named after mountain ranges on Earth. So that little mountain range that you see right there is the Alps. And then to the right, right at the rim of the Imbrium Basin, to your right, Rick, right there, and that mountain range going down, that's the Caucasus. And then right at the bottom of this image is the my brain is going blank on me here. Yeah, I forget. Apennines, that's what it is, the Apennine Mountains. So those are mountain ranges named after mountain ranges on the Earth. So let's go down a little bit. So you see another smooth floor crater called Archimedes, just above your cursor.
There we go.
There you go. And then down and to your right is another mountain range. That's the Apennines. All right. We'll go down a little bit farther to the bottom of the Imbrium Basin. And you just had your cursor on a crater there, right there. That's Eratosthenes. Eratosthenes is named after the first person to measure the circumference of the Earth. And this was back about around 300 BC. Eratosthenes was a philosopher in Alexandria, and he figured out a way of measuring the circumference of the Earth. Now, his measuring equipment was kind of crude.
It was a stick, wasn't it?
It was a stick in the ground, plus a well.
And no, he did not take the stick and just lay it out.
No. So what he
length
did,
by length until he circled the entire Earth.
What he did, he was aware of a well that was about 500 miles south of Alexandria in a little town called Syene. And in Syene was this well that was straight down. And one of the distinguishing things about that well was that every year, on one day out of the year, the sun would be straight overhead. So it shone straight down the middle of the well at noontime. So what he's decided to do was to set up a vertical stick in Alexandria on the exact same date and time and look at the shadow of the stick. Now, since the stick was about 500 miles north of Syene, its shadow was not straight down. It cast a little bit of a shadow. And by measuring that shadow and the angle between the top of the stick and the shadow on the ground, he used that to estimate the circumference of the Earth. Now, again, his measuring technique, he didn't have very good measuring tools, but his reasoning was sound. And had he had much better measuring equipment, he would have got an even better number. He got a pretty good number, but he would have got even a better number had he had better measuring tools. But again, his technique was sound. And one of the things this tells us is that people a long time ago realized that the Earth was round. There's a popular misconception that it wasn't until Columbus sailed across the Atlantic that people realized that the Earth was round. But that's not true. Long before that, astronomers and philosophers realized that the Earth was round. So that's the crater Eratosthenes, named after that guy who measured the circumference of the Earth. Coming down here a little farther, really interesting crater, right where your cursor is. That's the crater Copernicus. And Copernicus is a more recent impact crater, and we can tell that because of its bright color. But also, if you look around the crater, you can see ejecta, material thrown out of the crater and splashed out in all directions, forming long lines that extend away from the crater in all directions. And that material is laying on top of the lava that oozed into the Imbrium Basin and other regions around there. And that tells us that this impact occurred much more recently than the Imbrium impact crater. Some interesting things to notice about Copernicus. If you look carefully in the crater, maybe we can zoom in a little bit. All right,
hang on. Kind of reframe a little bit.
Yeah, hang on here. Okay, so if we look inside the crater, we can see it has a central peak. And this is very common for larger impact craters on the moon. That central peak is caused by what we call a rebound peak. And what happens is a big asteroid hits the moon, compresses the ground directly under the impact point, throws material up or out to either side to form the rim. And once the impact energy has dissipated, that compressed ground underneath rebounds back up. At the same time, all that material that was thrown up on the rim, some of it slumps back down. And those two combined effects produce the rebound peak, that central peak in the middle of the crater. We see those rebound peaks on larger craters. Smaller craters, such as the little one directly to the left of Copernicus, are what we call simple craters. They are just like a little bowl, and they don't have a central peak.
So, Gerald, would it be safe to say that the rebound peaks are kind of a mixture of material of the original crust that was there, plus the broken up material from the impacting asteroid or meteor as well?
Correct, but that material at the bottom of the crater, it's highly fractured and jumbled. So it may have been nearly solid rock when it got hit, but the impact just totally fractured it into little pieces and, of course, compressed it down. But as soon as that compression energy was released, it bounced back up. But at the same time, some of the material was pushed out to the sides, forming the rim of the crater. And again, once the impact energy dissipated, that material slumped back down. It also formed terraces around the rim. And if you look around the rim, you can see that there's a terraced effect. And that's very common for impact craters of this size on the moon. All right. Okay, well, let's go a little farther south. See what else we can find here. Okay, so this large region that's below Copernicus, that's called Mare Insularum. And there's a couple of interesting craters there. Schroeder, Gambert, a few others down there. But off to the right, it's kind of hard to see because it's in bright sunlight. But you see a formation there, a smooth crater to the right, to your right.
All the way to the
All the
right.
way to the right, almost right at the edge.
Oh, this
right
there.
There we
right
go.
there.
Yep.
That's Ptolemaeus. And Ptolemaeus is part of three craters. You see another crater just below it. And then a third crater down and slightly to the right, that one there. Those three craters make up what we call the snowman. So quite often when we're looking at the moon with certain kinds of telescopes, the telescopes invert the image. And when this image is inverted, it looks like a snowman.
Yeah, there's even a carrot. In the if you look at the bottom one there, that would normally be the head.
Carrot right there.
Right, and it's got one up from that.
One up.
Yeah, there we go.
This one?
No, to the right. There we go.
Oh, right there.
Right there.
Okay.
That's got the central peak that we were just talking about, and that would be the nose. Anyway, enough of that.
That's good. It's a vivid imagination. I like that.
Yeah. Well, I do.
So going left again from Ptolemaeus.
Okay.
You're going to come to a kind of a smooth region. Go down a little bit and right up a little bit. A little bit more, just above right there. Okay, that's called Frau Maro. And just at the northern rim of that is where the Apollo 14 landing occurred.
Oh,
okay.
That was the mission commanded by Alan Shepard. And if you ever go back to the moon and you happen to be in that area, you might want to look around, see if you can find a golf ball.
Yeah, there'll be a golf ball, and there'll also be a rover, right?
Well, I'm still looking for the flag.
Apollo 14 did not have a rover.
They did not have a rover. It wasn't until the next one. Okay, got it.
Apollo 15 was the first one that had a rover.
Yeah,
so right in that region right there. Yeah, that's
you'll find a sand trap, a golf ball, and a golf club.
So Alan Shepard was really into golf, and so he devised a very simple golf club that he could fold up, and he brought it with him to the moon. And during a free moment, he set the golf ball down, and with this golf club, which because of this big bulky suit, he could only hold the golf club with one hand. But he took a swing, sent the golf ball flying. The moon's gravity is only 1/6 of what it is on the Earth. So that golf ball flew a long way. So your mission, should you decide to accept it, is to go find
a golf
ball on the moon.
Okay. We have a couple good questions.
Okay.
Larry asked, why do all the craters, well, I wouldn't say all, but why do so many of the craters look like it's a perpendicular or 90-degree impact. And how come we don't see more kind of oblong craters or craters that look like they've been, caused by a glancing blow?
It's a great question. And the answer is they are not caused by perfectly vertical impacts. One of the strange things about the way impacts occur, and we've demonstrated this on Earth many times, is that even if a asteroid hits the moon at, say, a 45-degree angle or even just 30 degrees above the horizon, it still produces a round crater. So the fact that the crater is round does not tell you that the impactor hit straight down. In fact, in most cases, it did not. But it's just a quirk of how the impact energy is dissipated, that it produces a round crater, even though it can be a relatively shallow approach angle for the asteroid.
That's really interesting.
Yeah.
So the only real clue about the angle is if we could see ejecta.
Exactly.
So if we see ejecta off to one side only, then we know the crater was caused by more of a glancing blow.
Speaking of which,
you're going to look at Proclus.
I did not want to do that.
What? It wasn't me.
We lost the
moon. It was me. Hang
on. You should probably zoom back out to make it easier on Gerald here. Let me know if you need an assist, Gerald. An eyeball on the you had it there for a sec. There we go.
All right.
We're going to look at
time.
That was exciting.
All right. Let's do this the slow way instead of the fast way. Okay. Okay. So
there we
demonstration of exactly what Rich was just talking about. Right in the middle of the image.
No, not there. Go to the right.
Oh, right there.
No. Go up.
See the big round basin?
You see that white spot? You see the white spot? There we go.
Right there? Okay.
Right there.
Let's zoom in.
There we go. Perfect.
Okay. It's kind of hard to see because it's in full sunlight. Maybe we can improve the focus.
Yeah, there we go. That's good. No.
Don't mess with the lighting.
Yeah, that's as good as we're going to get the lighting. It's just so bright.
Yeah.
Okay.
Yeah. So that is called Proclus, and Proclus is an impact crater produced by a shallow angle impact. And if you look at the ejecta pattern around Proclus, you can see that it's all spraying out to the side and all forward, but there's none toward down and to the left. It's all up and to the right or out to the sides. And so what that tells us is that the impactor hit the moon traveling from the lower left to the upper right. So in that direction.
Boom.
And it hit at a low angle. So all of the ejecta sprayed out in sort of downwind or downstream of the impactor.
Yes.
But this is typical of a low angle impact on the moon. The crater is still a round crater. All right. So really good question. I'm glad you asked that.
Yeah, that was a great question. Let me see. We got another one, which was somebody was asking if we could see roughly the site of the Apollo 11 landing.
We could.
And I think we
just
should be able to see that. Yep.
Yeah, we just passed it. Let me get you over here and down a little bit. And then, Rick, if you can zoom in a little bit.
There we go.
A little bit more. Okay, what you're looking at, that big, huge, dark area, is called the Sea of Tranquility. And just above where Rick's cursor is, go up a little bit and to the right just a little bit and down a little, right in that area there. That is where Apollo 11 landed. Now, the hope was that that would be a very smooth area. That was going to be the first landing on the moon. So they didn't want to make it any more complicated than they had to. So telescopic observations and ranger and surveyor observations suggested that that was a relatively smooth area. It turned out, however, that it wasn't quite as smooth as they thought. As Apollo 11 was approaching the ground, Neil Armstrong was looking out the window at the site where he was supposed to land, and it was covered with all kinds of big car-sized boulders. And he didn't want to land on a bunch of boulders, so he had to take control of the spacecraft and fly it for quite a way. He flew it almost 5 miles before he finally found a spot that was smooth enough to where he could land. So that's the site of the Apollo 11.
That sounds like it would have been terrifying.
Yeah.
Yeah, they were also really low on fuel.
Yeah, they only had 20 seconds.
20 seconds.
20 seconds left of
Wow.
fuel. And so it's like if there was nothing but boulders, I don't think there was much of an abort plan at that point. Another really good question. We got really good questions tonight. How are the mountain ranges formed? Because there aren't plate tectonics on the moon. Lydia was asking, is it the same as the Earth with plate tectonics? Well, we know that there isn't plate tectonics. So how are these ranges formed? Some of them are pretty big.
So let's just look at one. We see one right in the center of the image, that mountain range there. That's the Apennines. All right. And if you notice, if you go along that mountain range, it's curved and it continues to curve upward.
Oh, yeah. Look at that. Yeah.
And it's curved and then it gets up. That's the Caucasus. And it continues all the way around to the left a little bit of your cursor. That's the Alps.
Makes a big circle.
Makes a big circle. That is the rim of the Imbrium impact basin. So that was a huge impact that occurred about 3.8 billion years ago. And it was a big one. In fact, if it had been much bigger, it may have destroyed the moon. That impact basin, of course, pushed material out to the side, just like the smaller craters, and produced a rim. And the mountain range that you see is caused by that impact.
Huh.
And that's true of a lot of the mountain ranges that we see on the moon. They're caused by the impact. Now, the moon also has much less prominent mountain ranges in the southern half that are just part of the older terrain of the moon. It's much more jumbled. It's more heavily cratered, but doesn't have big basins like the northern part of the moon does. And we can kind of slew on down. I don't want to take up the whole evening here doing just the moon.
Yeah, but that's the part of our camera presentation that works right now. So
you may want to reconsider that, Gerald.
Okay. So here now you're looking at the southern part of the moon, and you see one basin up into the left there a little bit. That's Mare Nubium, and then below it, it's all just jumbly mountainous terrain, but it's all because of lots of impact craters, but no big impact basins. So the mountain ranges on the moon are caused by impacts, not by plate tectonics.
All right, very good.
All right.
Related to that, I have a question related to that. Did the lava flows from early in the moon's history, where some of these mare were formed, did they back up and form any low mountain ranges, or is it pretty much just smooth terrain from the lava flows, and any ranges we see are impact created?
Well, let's see if we can kind of make sure I push the right button here. I almost did.
Sorry, I'm getting deep into the geology here. These questions really have piqued my curiosity, so to speak. No pun intended.
So let's see if we can see it here, or if we can zoom in.
Yeah.
I'm not sure how well we're going to see it. Yeah, I don't see it very well here. Sun angle is probably not right for this. But what we often see is that the lava, as it oozed up into these basins, it didn't happen in one continuous episode. It happened in multiple episodes, and that caused small wrinkle ridges, if you will, to appear in many of these basins. There's one I was trying to get to called the Serpentine Ridge, which is a really interesting one, but it looks like we're not going to be able to see that. Too much light on the moon.
I got it. So
Light is,
Okay.
well, we should revisit that sometime in the
Yeah,
future when the
yeah.
lighting is right, because I think it's really an
yeah, the
interesting
Serpentine
process.
Ridge
Yeah.
is really cool. You'll see it as soon as you see it. You'll know why it's called the Serpentine Ridge. So,
All right. Cool.
I want to go back down again. Maybe just do one final crater here because it's such a prominent crater. If you look a little bit to the left, there, up, right, up, too far. We're looking at Tycho.
Oh.
Tycho, right there. All right,
there.
so that is the Tycho impact crater. And one of the distinguishing things about Tycho, it's a relatively young crater. It's maybe 100 million years old. That's young. But it was a very dynamic impact that produced these very long ejecta rays. And if you look around, especially to the right, you can see these ejecta rays extending out hundreds of miles in all directions. And those rays are even visible in binoculars when you look at the moon, especially at this time or at this phase of the moon. You can see it just really well. Yeah, making it brighter doesn't really.
Yeah.
Yeah, you need more contrast rather than.
More contrast rather than brightness. Yeah.
But again, you take a pair of binoculars, look at the moon right now, and you could probably see some of those ejecta rays, and they literally extend hundreds of miles from the Tycho impact crater.
That's actually that's a feature where less magnification actually helps.
Right,
really.
right. Yeah, sometimes the best way to look at the moon is not with a really powerful telescope, but just with a pair of binoculars or a smaller, less powerful telescope. A lot of cool things to see that way.
Hey, Gerald, can you just maybe elaborate for a little bit on one of my favorite craters, which is Clavius?
Clavius,
down here?
yeah.
It's got to be one of the most interesting craters on the moon. It's a crater with multiple craters.
Lots of craters inside. Yeah. So Clavius is sort of a middle-aged crater. I think it's about 2 billion years old. But one of the things, as Rick was saying, that distinguishes Clavius, it's a relatively big crater, but inside of it are several much younger craters.
Can we recenter?
Yeah, sure.
You should be able to you could just drag the image, Rick. You should be able to. There we go.
All right. Yeah, so maybe zoom in a little bit. Now, when you look at the craters inside, a couple of these craters actually look like they were part of the same impact event. So if you go up, let me see if I can focus a little bit better here.
Are you suggesting it's like rock skipping?
Oh, better. Yeah, much better.
Yeah, there we go. All right. So you see the one that's right at the rim at the bottom right. All right, that's not it. But above that, and just slightly to the left, that one, the one to the left of it, and to the left of it, and to the left of it.
Oh my, yeah.
There is
each
a
one
possibility
is a little bit smaller.
That might have been part of an asteroid that broke up prior to impact.
Oh.
Either that or it was some kind of a bounce. More likely, because they're not in a straight line, it was more likely chunks of the same asteroid hitting almost simultaneously. So, really cool.
That is, yeah, it's got to be my favorite crater. I had always assumed it was multiple hits, but not from an asteroid breaking up. Or that's just.
Well, we don't know that for sure. It's just that those all look very similar in age, and so that's one possibility.
And they they form a very continuous arc.
Yes. Yeah.
That's another clue.
Now, it is a fact that we often see this, either a broken up asteroid where several pieces hit the moon almost simultaneously and produce a little chain of craters. But more often, what we see is when you get a big impact, big chunks of rock fly out of the crater. And then they fall back down and they produce what we call secondary craters. And quite often, those secondary craters are actually themselves crater chains. So instead of them just being random, they're all lined up. But that line extends backward towards the crater. There's actually a couple of those near Copernicus. I'm going to go back up again and see if I can. Not sure if we're going to be able to see it or not.
There's a chain right there.
Yeah, well, I want to go back up to Copernicus here.
So just like we have asterisms, we have craterisms. You're looking for patterns of craters now.
With a really powerful telescope. Why don't you see if you can zoom in now?
There we go.
Keep going. Let's see if we can pick out any of those crater chains. Yeah, focus isn't quite good enough.
No.
Oh well.
You could try brightening it up a little bit. Maybe they'll pop out. And just go down to there we go.
I'm going to play with the focus a little bit and see what happens.
Yeah, I don't think we're going to get much better than this.
Get worse?
It can get worse. It can always get worse. While you're doing that, we had a couple of other good questions. Can you speak to the predominant mineral content on the moon?
An orthosite. An orthosite is a mineral. It's called plagioclase feldspar, which is a common rock on the Earth. But in those white regions that you see, the dominant rock or the most common rock that we see is called an orthosite. In the dark areas, it's basalt, just like basalt on the Earth. So it depends on where you're looking. When you look at the moon, you see dark areas and light areas. The light areas are an orthosite, and the dark areas are basalt.
So two very common types of minerals that we find here on the Earth.
Right.
Have there ever been any? Has there ever been any indication of more specialized mineral deposits on the moon that are a little?
Yeah. There's those are the dominant ones, but there are lots of other minerals on the moon. I mentioned. Plagioclase feldspar. There's several different types of feldspar. What else is there on the olivine? There's some orange crystals that are actually volcanic crystals. I can't off the top of my head remember very many of them, but they're all minerals that we find on the Earth. They're up there on the moon as well. So, if you want to, open a mine on the moon.
Transportation costs are high.
Oh, so Rick, stay zoomed in.
Okay.
Zoom back in. Okay, because there is one chain of craters right where your cursor is.
Up here?
See a little arc of very
yeah.
Oh, yes, right there.
Right there.
Let's move that into the center.
Yeah, so those are actually secondary craters that came from the Copernicus impact. And there's a lot more of them around there. Cool. It's just very hard to see.
Yeah.
All right.
So unlike the Earth, there isn't much erosion on the moon, but there is some erosion caused by other impacts. So impacts erode other impacts. But we don't have any water, so there's no real erosion. There's no rain, there's no wind. There's solar wind, but that doesn't erode much. So I hope that answers Larry's question.
Yeah, so somebody asked if all of the impact basins, the big basins, were produced when the moon had a molten core. If it's filled with lava, it had to have happened when the moon still had its molten core. So again, these are big impact basins, and what happens is there's a molten interior, lava oozes up and fills the basin. Once the moon's core cooled to where it was no longer molten, any subsequent impacts would not produce that infill from lava. Now, there's a lot of debate still about whether the moon's core is completely solid. There is some occasional indication that there may be some very localized volcanic activity still going on the moon. But for the most part, the interior has now solidified. The moon is much smaller than the Earth, so it cooled more rapidly than the Earth.
All right.
All right.
So if I've got an idea here, Gerald, why don't you talk about what's going to be happening on the 30th? There's an event, special event for Asteroid Day. And while you're doing that, I'm going to see if swapping out the computer helps us with our camera issue for taking longer exposures. And then we'll decide what to do with the rest of our time tonight. All right, great.
So let me stop sharing right now.
All right.
Okay.
I guess that means I have to share. So let me change my glasses again here. So what Rick was telling you about, on June 30th, Chabot Space and Science Center, along with many other science centers and observatories around the world, we will be celebrating Asteroid Day. June 30th is Asteroid Day. June 30th is the date of a big impact that occurred in Russia, near a region called Tunguska, in the year 1908. About a 50-meter asteroid that explosion was so forceful that it flattened a huge region of the forest in the Tunguska region. So that was a very powerful impact, so powerful that seismometers all over the world registered the impact. And what more recently we astronomers decided to do is kind of create a day where we could just sort of emphasize the fact that asteroids do hit the Earth occasionally. And so we decided that June 30th, the anniversary of the Tunguska impact, would be a good day to do that. So here at Chabot Space and Science Center, starting at 7 o'clock in the evening on June 30th at 7 o'clock Pacific Daylight Time, we're going to host a virtual program. We're going to have a couple of really interesting interviews. One of those interviews will be with Dr. Ed Liu, who is a former astronaut and is now on the executive board of the B612 Foundation. The B612 Foundation is an organization that was formed by former astronauts and cosmonauts. One of the other astronauts that you may be familiar with is Rusty Schweickart. He is an Apollo astronaut. And they formed the B612 Foundation specifically to advocate for continuing research into asteroids, in particular the near-Earth asteroids that could possibly impact the Earth someday. So Ed Liu will be one of the people we'll be interviewing. another professor, his name is Prettyman. He will be talking about Earth science and how asteroids have affected Earth science and the history of the Earth in the past. And then I will be doing a demonstration of how we search for near Earth asteroids, because the telescope that we're using here tonight is also the telescope we use to do near Earth asteroid searching and tracking.
All right,
So that's
thanks.
coming up on
Yeah.
June 30th.
That's great. Yeah, thanks for explaining all that, and I hope some of you can join us. We have good news. We've got the camera working the way we want it to. Basically, we have to fire the consultant, which would be me in this case. So we now have it set up properly. Gerald, we got a lot of choices for what we might want to look at tonight, and it would be nice to pick out maybe a couple of bright objects.
All right. Are you still on the moon?
Yeah, I think we're still on the moon. But I was thinking maybe we should swing over to Lyra and look at the Ring Nebula, perhaps.
All right. Let's see. Let's make a little hop, skip, and a jump here, because that's a little bit of a trip there.
It is a trip, but that's where everything cool to look at is tonight, right around there.
Well,
you know, the bright stuff that's away from the moon.
So I'm going to take us to Arcturus first. Let me change tracking rate. And we'll use Arcturus to help us get synchronized. Are you in live view?
Yes, we should be in live view here.
Yeah.
Let me up the ISO.
Yeah.
Frame and focus.
Hey, Rick, you might want to
I'm not seeing it in the Finder either, so.
Oh, I don't know what just happened here.
Yes, I'm seeing stars.
You're close, but it's not in the Finder view yet.
Okay, something just went crazy with the computer here, guys.
Well, it seems to be the trend tonight. So.
Okay, yeah, we just lost our computer control for the telescope.
Oh. Well, that doesn't bode well.
Okay, nope, I got it back.
Yeah. Maybe it's me standing too close. I might have a field surrounding me tonight. So.
Okay, can you see through the telescope at all through the Finder?
Through the Finder, I am not seeing the target.
All right. Well, then bear with me. Keep talking for a second here, and I'm going to go.
But we are close. Rick, you have the hand pedal? We're doing it the old-fashioned way, eyeballing it. It looks like, no, I'm not seeing the glow. That's the thing. Yeah, take a look. Well, maybe a silly suggestion would be to slew back to the moon, center, sync, and try again. Okay. Maybe not such a silly suggestion.
Stay there
Yeah.
Center it up.
All right.
Okay, we got something strange is going on here.
Well, it's moving. That woke me up.
Surprise.
The eyepiece poked me in the eye. So, Rick, I've noticed that you show up here when the skies and the seeing are really good and the humidity is low. So either you're really good,
That's funny, isn't
you're
it?
really good, you're really good luck for this process,
Yeah.
or you're cherry picking your nights, and I haven't decided which it is yet. Ah, okay. We are close to the moon, not quite. Let me see if I can get that.
Gotta reduce that.
Okay. Are you in live view by any chance, Rick?
Yeah, it should be in live view right there.
All right. Yeah. So you should be seeing the moon coming into view.
Drop the. There it is.
All right. So tell me if it's more or less centered in the in your field of view, Rick.
Yeah, it's getting there.
Okay.
Yeah,
All
I'd say
right.
right about there.
This seems like a good place to sync, Gerald. If you can. All right, let's try for Arcturus again then. All right. All right, that's much better.
Look at there. There
Dead
we
center. All right.
There we go. All right.
All right, Arcturus. Follow the arc to Arcturus.
Let's see. Do we want to stop at M13 first, or should we?
Yeah, let's do that. Why not?
All right. And here we go. M13, Globular Star Cluster. I'm going to let you guys do some of the talking here. Give my voice a rest here.
All right, Rick, you're probably going to want to do 20 or 30 seconds. And it's not going to work for live view, so you have to go to exposure.
Okay.
And yours is a more sensitive camera than mine, so you could try 20 seconds maybe.
Let's try this. Try 5 seconds just to see if we have it at ISO 25,000.
Oh, on live view?
On live view.
Oh, just to see. Yeah, that would be interesting. Yeah, I've never gotten that to work on the longer exposure stuff. You've got to go.
Hey,
yeah, it did work though.
Is.
Oh, there we go. Okay, it works with this one. That's nice. All right, so what we're looking at is M13. Now, there's a lot of objects in the sky that start with M. You're going to hear us talking about M13, M101, M5, M3, and what's that M? That M stands for Charles Messier, who was an astronomer in the 1700s, and he was one of the first Western astronomers to put together a catalog of interesting objects. And he was mostly hunting for comets, but would constantly come across objects in the sky that were not comets. And so he, in order to not be confused during future observing sessions, he would catalog them, where they are, which constellation they're in, what they look like, how bright they were. And that Messier catalog is still used today among hobbyists as a great list for targets. And also, Messier objects tend to be the brighter interesting objects in the sky, because if you think about it, in the 1700s, the 1800s, the telescopes weren't that big, and so we were discovering star clusters like this only if they were bright enough to be seen. So what you're looking at is the globular cluster, and a globular cluster is a large number of stars. We're talking tens of thousands or hundreds of thousands of stars, all gravitationally bound in a kind of a ball of stars in the sky. And they were all formed out of the same what's called the molecular cloud. And a molecular cloud is a region of space that's very heavy in hydrogen, and that hydrogen coalesces into stars. And if there's enough of that hydrogen, you get lots of stars. And with huge amounts of hydrogen, you get these globular clusters. And so these stars formed around the same time in the vicinity of one another. They're gravitationally bound, like I said, so they orbit around each other. And if you were to look up in the night sky, if you were centered in this globular cluster, you'd have a very bright sky. The sky would be filled with extremely bright stars, and you wouldn't be able to really see much in the space beyond. Now, this globular cluster is, Gerald, if I remember correctly, it's in the 30 to 40,000 light years away.
25,000 light years away.
25,000 light years away, thank you. And contains several 100,000 stars. And I know that a couple of weeks ago you were convincing me about what part of this cluster has the propeller. And
Yep.
I'm wondering if we can up the contrast a little bit.
No,
Rick.
I can see it now.
I can never make this thing out.
I can see it now.
Oh, I see it now. Yeah, okay.
Lower
so
left.
Yep. No, that's too much
no,
contrast.
too much.
Yeah.
That's true. Well, wait a minute. Now what happened?
Yeah. Now it's all messed up.
Now it's all messed up. Yeah, I've done it now. You may just have to snap another image.
We can see it.
Can you see it?
Yeah. You might shoot another image.
Let's.
I'm snapping another image right now.
Yeah, those. You got to be careful with those sliders. Sometimes they cause permanent effects on the image, and you can't get out of it.
Yeah,
okay.
Exactly
so let's look at this now. You kind of point to the center of the cluster now, Rick. All right, and then just down and to the left of there, you'll see a 3-bladed prop. There's the hub, and straight up from the hub is one of the blades.
Yeah, right. If you move the square a little to the left.
No, Rick.
Move the square to the left.
Dark 3-bladed prop.
Keep going there. Now you're in dead center.
All right.
So if you move up from there.
Oh, I see. So it's
there's 1, 2,
and
3.
There you go.
So what that propeller is, there isn't actually a propeller on M13.
Are you sure?
It's not like a giant spaceship that goes through space with a propeller, but it is a dust cloud that obscures part of the globular cluster and appears to us from a distance as having a propeller shape. And it's just one of the distinguishing features of M13. Not all globular clusters have thick dust lanes blocking part of them. and it's just one of the fun things to look at with M13. Now, the other thing about globular clusters, I mentioned how they all formed, all the stars in a globular cluster formed from a single large dense molecular cloud. These are also really old stars. Now, the typical age of the stars in a globular cluster are in the 13 billion year range, and those are among the oldest stars in the known universe. So globular clusters are very, very old objects and have what are very pristine materials. So it's only hydrogen and maybe some elements slightly denser than hydrogen, but they're not like our sun, which contains many different heavier elements like helium and other intermediate elements. So it's considered what astronomers call a low metallicity type of star, meaning it does not have heavier elements, and that's how we know they're so old.
There was a question on Facebook that I might want to answer here.
Sure.
The question was, how many Messier objects are there? And there are 110 Messier objects. And in fact, in March, a lot of astronomers like to do what's called a Messier marathon. Because in a certain period, about a 3-week long period in March, if you want to stay up all night, you can see all 110 objects, but you got to start just as soon as it gets dark, and then you stay at it all night till about 4:30, 5 o'clock in the morning, and that would allow you to see all 110 objects.
If you're lucky. Now, the thing is that Charles Messier did not catalog all 110 of those objects. A lot of those objects were added much later, some even in the 20th century.
Yeah, I think there was only 102 or 104 or something.
Yeah, it was like 102, I think, and the others were added later, just kind of in honor of his effort. There were also some confusing objects like M101 and M102. There was a lot of confusion on whether he had actually double counted M101, and then it was decided that there was another galaxy that was probably bright enough that wasn't too far from M101 that was then labeled as M102. So there's some ambiguity in the actual number of objects that Charles Messier may have actually seen, but nonetheless, we have a nice 110 object catalog to work with.
All right. Well, speaking of Messier objects,
let's look at another M object.
Skip on over to the Ring Nebula, M57.
Yep.
All right, here we go.
So, Rick, this one is probably deserving of an actual image of 30 seconds or so.
All right, we'll just frame and focus here as soon as we're slew the telescope. Okay.
All right, we're there.
All right.
So, what we're going to look at now is the remnant of a dying star. Most stars die a very gradual death.
Oh, very nice.
Wow, that was fast.
Yep, that's great.
Yeah, let me reposition here a little bit. All right, you can try it again if you want.
Sure.
A lot of red in this one.
Yep.
Yeah. Well, the camera is bringing that out too.
That's right.
This is an astronomical camera, so it doesn't have that pesky red filter in it. So yeah, this is the camera that Rick is graciously letting us use tonight is designed for astronomy. It's a DSLR camera, but it doesn't have the same filters on it that standard DSLR terrestrial cameras have. When you go out and you buy a camera at Costco and take it home, there's an infrared filter on that camera that makes the colors of the world around you look natural. but that infrared filter gets in the way when you're shooting astronomical objects. So this is a special DSLR camera that doesn't have that filter and makes it very well suited for things like the Ring Nebula. And
Yeah,
that's
actually, Rich, the camera has a special filter that makes it more sensitive to those nice red, pinkish colors of hydrogen, but it still can be used in daylight, which is
you don't have to add
really
an
nice.
extra filter to this one?
No, it's factory calibrated, and that's what is
That's
so nice
pretty
about
neat.
it. Yeah.
So they fixed that in software, I guess.
Okay, well, this object called the Ring Nebula is also designated M57, so it's number 57 on Messier's list. And the Ring Nebula is the remnant of a dying star. So this was once a star, probably very similar to our sun, but when the star got old, it swelled up and became a giant star. And as it swells up, it cools, and its gravitational hold of the outer layers of gas of the star weakens. And also, you get a lot of turbulence going on within the star. Also, a lot of pressure resulting as the gas gets less dense. You get a lot more radiation pressure coming from the interior, and that causes a very strong wind to blow the outer layers of the star out into space over tens of thousands of years. And eventually, the fusion process at the core of the star stops, and whatever's left of the star becomes what we call a white dwarf. White dwarf is kind of a collapsed version of what's left of the star. It's extremely dense. It's right there at the center, just barely discernible. So this star may have been 1,000,000 miles in diameter when it was in the prime of its life, but all that's left now is a white dwarf, which might be only 10,000 miles in diameter. The white dwarf is surrounded by all that gas that it was blowing off when it was a red giant. And the white dwarf, because it's so small and compact, it still has all the residual heat left from the star. And it because it's so small and compact, it radiates that heat, very high energy. It's very, very hot. And so a lot of that energy is radiated as ultraviolet radiation. Ultraviolet radiation goes out, ionizes all that gas, and causes it to glow. So most of that gas is hydrogen. And if you notice a kind of pinkish color around the fringe, that's because of the hydrogen gas. But a little closer in to the white dwarf, there is some oxygen. And there's a certain kind of oxygen called oxygen 3, which is most stable out in space, but very hard to make stable in the laboratory.
Isn't that what they used to call nebulum?
Yep.
Nebula.
So when astronomers first saw this, they weren't sure what gas that was. And so they gave it the name nebulum. And it wasn't until much later that they realized it was just a certain version of ionized oxygen. Now, because it's so green, you might think, well, gosh, there must be a lot of it there. Well, it turns out that ionized oxygen, this particular type, glows extremely brightly in that kind of greenish blue color when it's ionized. And so that color dominates the pinkish color of the hydrogen. There's actually more hydrogen there, but the oxygen that is there glows much brighter. So this is called a planetary nebula. It has actually nothing to do with planets. But when astronomers, 150 years ago, when they first started seeing these things, they actually thought they were gas clouds that were condensing to form new planets. It wasn't until later on that they realized this was actually the end of the life of a star.
Yeah, they didn't realize how far away these things were.
Yeah.
And do you think there's another object not far from here that I've been dying to have us try, And I'm wondering if we can.
I'm wondering before we move off,
Huh.
if these stars are bright enough to maybe
We lost you.
We just lost your audio, Rick.
Oh,
Yeah.
It's back.
I don't think those are bright enough to focus on, and probably we'd have to go to a brighter star if you wanted to refocus.
all right.
But if we can go to NGC 6826,
And by
and that's in Cygnus, and I think it should be high enough.
NGC 26.
No, 6826.
Being very cautious with my software here. It was acting up on me a while ago.
Yeah,
so.
I saw that. Yeah.
All right, here we go.
Now this is a dimmer object, Rick. So
yeah, we're stretching your cable quite a bit there.
I'll check the cable.
Yeah, it looks like you're okay.
Yeah, we're good.
All right.
All right. We won't go any farther than that because
okay.
I don't want Rick to be dangling from the telescope.
I can't. Gerald, can you use the fine focus to maybe focus on that?
That may be our target.
Oh,
so.
All right. Let me do.
Why don't you, since it is a nebula we're looking at, let's not worry too much about the fine focus. And let's see if we can.
Okay, we'll come up with an image here in about 1 second, maybe 2 seconds.
Maybe 3.
Ooh,
there we go. Okay.
3 seconds.
So
yeah.
this is another example of a planetary nebula. You notice this one's a lot smaller than the ring, and that's because it's farther away. This one is called the blinking planetary. And the reason it's called that is when you are looking at it visually through a telescope, and I've looked at this through, a 10-inch and a 14-inch telescope, the central star, which you can see there in the as a bright white spot in the middle of the nebula, that central star is not visible when you look at it straight on with the naked eye. But if you use averted vision, which means look a little bit to the left or look a little bit to the right while you're still concentrating on the planetary nebula, then that central star pops out because the edges of your vision are more sensitive to light than the center of your vision. The center of your vision is sensitive to color. The periphery of your vision is sensitive to dimmer light and to motion, actually. And it's a survival thing, I guess. You want to see the mountain lion crossing into the periphery of your view. So we put that to our advantage in visual astronomy by using something called averted vision in order to see greater detail. And the blinking planetary is a really well-known object for demonstrating averted vision and for putting it to use. Anyway,
all right.
That's the blinking planetary.
So someone on YouTube asked if it's possible that the sun actually has a binary companion that's a 5 billion year old dark dwarf. It's possible.
Yeah, maybe it's Planet X.
It would have to be very far away, otherwise we would see the gravitational effect.
Right.
But
But but it's not. It's a really interesting question, and everything. It seems like everything in the universe is part of a continuum of scale and examples of different phenomena. And so probably rather than us being a binary system of multiple stars, what we are is a system of a large central star and large gas giants, which if those gas giants had been bigger, if Jupiter had been bigger, then it might have gotten big enough to turn into a star. And then we would be a binary star system. But because it didn't get that big, what we have are large gas giants instead. So it's a continuum. So half the stars in the visible universe are binary stars. When you look up and you see a pinpoint star, there's actually probably 2 stars there. I mean, this is 50% chance. So they're not unusual. They are pretty run-of-the-mill, and the solar system, just through the odds and the physics of the formation of our solar system, ended up as a single star with large gas giants rather than binary or triple system.
All right. Well, guys, it's 10:45.
Yeah. But now we're starting to have fun looking at these.
Yeah, listen.
Well, that's the problem.
Harold.
We have a significant date coming up 2 days from today. It's the solstice.
Yeah.
So at 8:32 Pacific Daylight Time on Monday evening, the 20th of June, which is 03:32 on the 21st in Universal Time in Greenwich, England. The sun will be basically at its highest point, the farthest northern point in the sky. So the sun for us will appear to suddenly stop and start going in the other direction. So what that means is if you look at the position of the sun above the horizon, just as the sun is crossing the meridian at noontime, it gets higher and higher each night between spring or actually between winter and spring for those of us in the northern hemisphere, and it gets at its highest point right around the 20th or 21st of June. And then as the year continues, it begins to get lower and lower. So each day at noontime, it's a little bit lower in the sky. And then for those of us here in the winter, somewhere around December 21st, the sun is at its lowest at noontime. So the solstice, the point where the sun changes direction from going higher and higher to going lower and lower, that will be at 8:32 p.m. on Monday, June 20th. That's 8:32 p.m. Pacific time. All right.
Well, thanks for that reminder.
Hey.
Yeah.
All right. Let's see if there's any other questions, and if not,
Any other objects?
yeah.
That also means
Alan
that
was telling us that it's 102 degrees in Las Vegas still right now.
Yeah.
Well, I'm glad he went somewhere this week to cool off. Good choice of destinations, buddy. What can I say?
And now the other thing about June 30th is it will be the longest day of the year. Longest day in terms of how long the sun is above the horizon. It's like 15 hours and 15 minutes or something like that. So I'm sure somebody will look that up. But
That was June 20th, right?
June 20th. Yeah. What
Yeah,
did I say?
there we go.
Did I say
And
January?
it's also one of those
Yeah.
days where those Paleolithic solar calculators tend to really show off. That's the particular time they were always looking for, is the summer solstice, the winter solstice, right?
Right.
So good. It's a good week to travel to Stonehenge.
There you go. Well, I'm looking to see if there are any other questions. I don't see anything else going on YouTube.
Yeah, I don't see anything new on Facebook here.
All right.
People are bragging about their low temperatures. Bob Schock is bragging that it's only 55 degrees on the Oregon coast. Well,
Who cares?
lucky you.
Yeah, lucky you, Bob. That's right. Of course, we're sitting here with jackets on, so that's.
I mean, I do want to mention to Bob. Bob is has done many years of optical consulting for our team here at Chabot, and is a master optician. And we follow his advice and his methodologies for cleaning the lenses on our historical telescopes. And yesterday we actually did a session and cleaned both Rachel and Leah's lenses. And I got to tell you, Bob, the water was evaporating off of the cotton balls before we can get them onto the lens. It's been so hot here. So enjoy your 55-degree Oregon coast weather, because we're really missing it.
Yeah. So Michelle asks if we can see Orion's belt tonight. Unfortunately, we cannot. Orion is a wintertime constellation, so we aren't able to see it now. But in November and December, sometime around there,
we'll come back to it.
Yeah.
Yep. We'll definitely come back to it. But it's good we can't see it now, because otherwise, we run out of things to see. We really need we really need stuff to not be visible now, so we can have a good list of things to look at in the winter. So we'll be what's coming up now are a lot of the interesting nebula that reside along the plane of the Milky Way. So in another month, we'll be able to look at a lot of interesting objects that are just beginning to rise now and get high enough in the sky. So we're going to be sticking with the summer objects for the next couple of months, and then get into the fall objects.
All right. Well, once again, just want to remind you, we are relying quite a bit on donations. So if you're on Facebook, there's a donation button on the page there. Otherwise, you can go to the Chabot Space and Science Center website. It's chabotspace.org. And you'll see a donate button at the top of the web page. Also want to remind you, if you work for a company, or if you know someone that owns a company that likes to support nonprofits, we would certainly encourage you to talk to them and talk to them about doing a corporate sponsorship or a corporate donation to Chabot. We would certainly appreciate that. All right.
All right. I guess that's it.
All right.
Okay.
Same time next week.
Yep.
9:30. Week from tonight.
All right. Everybody enjoy the rest of your weekend, and we'll see you next time.
Bye, everyone.